Okay, again, we are on page 23 to start for today. Yesterday, you guys had that activity on Desmos where you were looking at sort of adjusting graphs of functions with those sliders. So we're going to talk about what you guys saw on that activity here in just a minute. But I want to start by talking about the idea that you had some sort of graph that remained the same on each of those pages, and then you had a graph that moved, right? So you adjusted the slider on the activity and you had a graph that stayed in place and a graph that moved somewhere else or changed somehow. That graph that stayed in place is what we're going to refer to as the parent graph. So the portion of the graph that you guys saw yesterday on that activity was, I think, a section of a sine graph. We have a couple of functions that we're going to look at as parent graphs in here as we work on transformations for the rest of the week. So I want to take a look at those parent functions to start, and then we'll talk about how we move those things around. Yes, question? Yes. Okay, so the first one we're going to talk about is a linear function. So a linear function is just a line. You guys have seen lines before. And for our parent function, we're looking at the most basic linear function that we can have. So no bells and whistles, just y equals x, or f of x equals x. And that's what we'll see for each of these parent functions that we talk about. No bells and whistles, no extras, just the most basic version of that function I could have. And I also want to briefly mention that each of these types of functions we'll talk about in more depth, I should say, later on in Algebra 1. Like linear functions we're going to look at in our next unit. Quadratics we'll talk about later on in the year. We'll see absolute value functions, I think, in Unit 4 maybe. But we'll talk about all of these in more depth later. All we care about for right now is the parent function. So I want to know what the graph of my linear parent function looks like. Anytime I want to graph something, I can always make a table, pick some values for x, and plug them into my function to see what I get for y. Okay? If you ever get stuck, you're taking a quiz or a test or a quick check or something, and you have to graph something and you've forgotten what you need to do, make a table. Go back to make a table. Okay, this will always work. So I'm going to pick some values for x, and I'm going to plug them in and see what I get for y. So if I plug in -2, then I would have f of x equals -2, or y equals -2. If I plug in -1, I would have f of x equals -1. If I plug in 0, I would have y equals 0. If I plug in 1 here, I would have y equals 1. If I plug in 2, I would have y equals 2. Once I've made a table, I've got a bunch of ordered pairs now that I can plot. So -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. And there's my linear parent function. So as we talk about transformations for the next couple of days, I'm talking about changes that I've made to that parent function. Next, we're going to look at our quadratic parent function. So a quadratic function is an x squared function. So this is our most basic x squared function. And I'm going to do the same thing. I'm going to plug in values for x. So I'm going to use the same ones, -2, -1, 0, 1, and 2. And I'm going to plug them in for x here. So when I plug in -2, I would have -2 squared. That means -2 times -2. -2 times -2 would give me 4. Then I would plug in -1 squared. Again, remember that means -1 times -1. So that would give me +1. 0 squared would be 0 times 0, which is 0. 1 squared is 1, and 2 squared is 4. So again, I have points that I can plot here. So -2, 1, 2, 3, 4. -1, 1, 0, 0, 1, 1, 2, 4. The graph of a quadratic function is called a parabola, and we'll talk more about those again later on in this course. But it's this sort of U-shaped graph We have sort of a center point here on our parabola. The next function we're going to look at is an absolute value function. So our parent graph here, our parent function is just the absolute value of x. And remember, for absolute values, that means I'm looking at the distance from 0. So I'm going to, again, pick some values for x, plug them in, and see what I get for y. When I plug in -2, that would mean I'm looking at the absolute value of -2. What's the absolute value of -2? 2. Yep. Absolute value of -1? 1. Yep. Absolute value of 0? 0. Absolute value of 1? 1. And then absolute value of 2 is 2. So when I plot my points here, for absolute value, I get a V-shaped graph. Absolute value has a V-shaped graph. Okay. And notice, kind of similar to our parabola where we had that kind of center point there, we've got that point kind of at the corner there at the center of our value graph. And then finally, we're going to look at the square root function. So our parent function is just the square root of x. And again, I'm going to make a table. I'm going to change a couple of the values that I use in my table though. So I've used -2 up to +2 so far. Instead of using 2's, 2 doesn't have a nice square root. So I'm going to use 4 instead. Okay. So instead of -2 and +2, I'm going to use -4 and +4. This is kind of a like work smarter, not harder moment. I don't know what the square root of 2 is. It's not a nice number. So I'm not going to use that one. I'm going to use something that does have a nice square root. And on this one, let's work from the bottom up. So I want the square root of 4. What's the square root of 4? 2. Square root of 1? 1. Square root of 0? 0. And now let's talk about square roots for just a second before we talk about these last couple. So the square root of 4 is 2 because 2 times 2 gives us 4. Yeah? The idea behind a square root is what number times itself gave me this. So if I asked you about the square root of -4, does anybody kind of want to tell me -2? Maybe a little bit? Okay. Here's the issue with using -2. That would mean that -2 times -2 should equal this. But what is -2 times -2? 4. It's 4, right? It's +4. So I have an issue with square root of -4. We're going to talk more about this issue later on in Algebra 1 and definitely in Algebra 2. For right now, all we care about is what the parent graph of this thing looks like. So for right now, we're just going to say we don't know the square root of -4. We don't know the square root of -1. They aren't things that we can worry about right now. So that means our parent graph looks like this. I'm going to plot the points that I do have. And our parent graph looks like that. It's got an end point and it goes off in only one direction. If you remember rays from geometry where it had a point and it went forever in one direction, that's kind of similar to what we see with our square root graph. Okay, so as we talk about transformations today, we're going to look at transformations changes on these parent graphs. Before we move on in our notes, I want to bring up the activity that you guys did yesterday so we can all together kind of take a look at what you guys saw individually. So I'm going to pull up that activity that we did. Here we go. This was the first one that you guys looked at. So you had your graph here, and then it was K that you were manipulating. And so if I move K to be a number greater than 0, what happens to our graph? It goes up, right? And so if I look, K is just over 4, and from the corner where we started to the corner where we moved, that's 1, 2, 3, just over 4, right? About 4, and this number is also about 4. The other thing I want you to notice is our little function right up here. It says f of x plus k. So I've got my function and then plus k at the end. And then if I move this back so that k is a negative number, where does my graph go? It moves down, right? This graph that I'm manipulating moves down. So notice again that my k is -3, and from the original corner, I have to move 1, 2, 3 spots to get to the new one. I want you to also notice if I were to plug in the value I have to k right here, that would be f of x plus -3, or f of x minus 3 would be a little bit more concise way to say that, okay? So this k value deals with movement up or down. And now let's get past a couple of the questions that you guys saw, and let's talk about h. H was the next one you guys looked at. So when I manipulate h, if I move h so that it's some positive number, where does my graph go? It moves which way? To the right, yeah. It moves sort of forward. It moves over here, right? Here's my graph. It's moved to the right. So my h value is positive 2.5 right now, and I've moved, it looks like 2.5 spaces from where I started. Now I want you to notice on my little function guy up here, it's f of x and then minus h, that x minus h part is in parentheses. It's grouped together. And it's also giving me minus as my sort of format here. So if I were to plug in h, it would be x minus 2.5. And my graph has shifted to the right. Now, if we make our h value negative, where does it shift? To the left, yeah. And so let me see if I can get it on -2. There we go. And so right now it's 2 spots to the left of where it started. If I were to plug in -2 for h right here, that would be x minus -2. We don't usually write minus a negative. What do we write instead? Plus, we write plus. So if I were to plug in my value for h here, I would have x plus 2 inside parentheses. That's the only part of today that's going to be a little bit tricky, are these left and right shifts. Okay, so let me put this away for a second, and let's talk about that for just a second more. So I want you to notice, and I got this up on the board here, I want you to notice that as we talked about that h value, the sort of default version we had was x minus h. And so when our h was positive, like when h was 3, if I were to plug that in, that would be x minus 3. When our h was negative, if I were to plug that in, that would be minus a negative, which would be plus. Remember, when h was positive, that moved us to the right. And when h was negative, that moved us to the left. Okay, but I got kind of the opposite thing going on in parentheses here. Okay, that's the only tricky part about today, is that on the left-right movements, my sign is kind of opposite of what I might intuit or what I might expect. Everything else is pretty straightforward. So if we talk about the movements that we see here, we kind of already talked about h up here. We know that a change in h moves our graph left or right. So anything grouped in with the x is going to shift us left or right. So when I say grouped in with the x, it could be in parentheses with x, it could be under a square root with x, it could be inside absolute value bars with x. If it's grouped in with x somehow, that's going to be a left or right translation. K is the first one that we looked at, and that's what moved us up or down. So K is going to move us up or down. So what we're going to look at today are these left, right, up, down transformations. We're going to start with this first example here on page 24. I want to identify my parent function because then I know what the original shape of the graph is supposed to be. Then I'm going to describe the transformations that are in my function, and then I'll actually graph that transformed function. So here I've got the absolute value of x minus 2 plus 3. Since I have absolute value here in my function, that means that my parent function was the absolute value of x. That was the original. That's what we started with. And remember, absolute value had that V shape. Now, we're not going to have exactly the same graph that we had on the last page for our parent graph because we've made some changes to the function, right? We started with plain old absolute value. That's our parent function. And then we did some stuff to it. Mm-hmm. These guys? Yeah. Those are my absolute value bars. So that's telling me if I were to like plug value things in for x, I would take the absolute value of whatever that was. Does that make sense? Okay. Okay, so I know my graph is going to have this general shape, but not be the exact same graph that we graphed on the last page. So let's start with this minus 2 inside those absolute value bars. What is that going to tell me to do? What change is that going to make? Mm-hmm. If it's negative, will it what? It'll be, yeah, that's the one where we kind of think of it as the opposite. And so then what direction is it going to move me? Up, down, left, or right? Yeah, it's going to move me to the right. This way. Okay, so this minus 2 here, remember, inside with x does the opposite. So and maybe that's not how you guys think of it. I think if it says minus, it should move backwards, but it doesn't, right? That's the part that I said was a little confusing here. So since it's minus, it's going to move forward. It's going to move to the right. So we'll move to the right, 2, and then how about this plus 3 at the end? 3 up, yeah. Up, 3. So just so we don't have to keep flipping back and forth, I'm in a different color going to just plot the points that we had on our parent graph on the last page, right? We had that V shape look like this. There's our parent graph. You don't have to put the parent graph on yours. I'm doing it just so I don't have to keep flipping back and forth between the last page and this page as we look at the parent graph. So there's my parent graph. I like to start with that sort of distinct point that we had talked about a couple minutes ago. So this sort of corner of the V is pretty unique, right? Easy to identify. So let's start with that point. I want to move it right 2 and up 3. So right 2, up 1, 2, 3. That point goes there now. And I do the same thing with every other point here. So I did that one. Now let's move this one. We're going to move it right 2 and up 1, 2, 3. This one does the same thing. Right 2, up 1, 2, 3. And these other points will follow suit. I get exactly the same shape, but my graph has moved to a new spot on the coordinate plane. You guys with me so far? Okay. Now, you talked about transformations in geometry. You weren't transforming functions. You were moving points, or you had like shapes, like you had a triangle on a spot of the graph, and then you shifted it somewhere else, or flipped it, maybe reflected it. These are the same types of transformations you saw in geometry. We're just doing them with functions now instead of with figures. Okay, let's take a look at our next one here. Square root of x plus 1 minus 2. So I want to start with my parent function. My parent function would be just the plain old square root of x. And remember, that graph looks kind of like this. It had an endpoint. It went forever in one direction. And again, in that other color, I'm just going to sketch our parent graph, just so that we remember what it looks like when we go to graph this new one. And now I want to talk about how I'm changing that parent graph. So this +1 under the root with x, grouped in with x, goes to the left 1, very good. And then how about the -2 at the end? Goes down 2. Okay, so I'm going to take this point and move it left 1 and down 2. I'm going to take this point and move it left 1 and down 2. I'm going to take this point and move it left 1 and down 2. And there's my new graph. As I said earlier, you can always default back to make a table, pick some values for x and plug them in. We could certainly graph this function by making a table. However, if I recognize the parent graph and the transformations here, it makes my graphing process a lot faster and, depending on the function, a lot easier. Yes. Yes. So this guy gets arrows. The only thing that doesn't get an arrow is this end on our square root graph. Because remember, we couldn't do square roots with the negatives. Okay. Other questions? Yep. Because he's going to keep going. Okay. Other questions for me so far? Okay. Let's hop to the next page. And we're going to kind of do this in reverse now. So we're starting with the graphs here. And we're going to create the equation. So for each of these, the solid graph is the parent graph. And we want to write the function for the child graph, which would be the dashed one here. So let's talk about the transformation that we're seeing here. So I'm going to use that corner to corner. I like to pick a point that's sort of easy to distinguish. How did I get from this point to this point? What did I do? How did I move? Can you say that a little bit louder for me? Down 3, right 1. Good. Down 3, right 1. Okay. And I've got this V-shaped graph here. That's absolute value. So my function then would be the absolute value of something. Down 3 will be a -3 at the end. Right 1 is going to go inside the absolute value with x. So to go right 1, we have to subtract 1. Remember, that's the one that's kind of opposite. You guys with me on this one? Okay, let's take a look at another one. So the next one that we have here is a line, right? And so I'm going to just pick that point on the origin there. Lines don't have those sort of distinct corners like what we saw in absolute value graphs, or an endpoint like what we have with a square root graph. I'm just going to pick the point that's on the origin. So can somebody give me a way that I could have moved this point so that it would end up on this line? Up. What do you say? I'm sorry. Up 2. I like up 2, and I like left. Left. So if we go up 2, we would go left 2. Okay, up 2, left 2. I like that. Anybody else think of a different way we could get there? Just up 4. 1, 2, 3, 4. That gets me on the line. Anybody have another way? Just left 4. 1, 2, 3, 4. That would do it. Up 1, left 3. Up 1, left 3. That would do it too. We have a bunch of different options here, right? Do you have another one? What do you got? Up 1, 2, 3, left 1. So let's take a look at what these functions would look like. So up 2, left 1. That would be, remember, this is a linear function. So I'm going to use parentheses just to group the left, right in with x. So left 2 would be +2. Up 2 would be +2. Up 4 means I would have x with a +4 at the end. Left 4 means I would take that 4 and add it right to x. So I'm going to group that in with the x. I'm just using I know it seems silly here. My parentheses probably do. I'm just grouping those side to side, those, in this case, left transformations, the same way we did for our other functions. Up 1, left 3, that would be x plus 3 plus 1. And then up 3, left 1, that would be x plus 1 plus 3. Do you notice anything about all these functions that we've written? Yeah. In every case, I could simplify and I'm going to end up with exactly the same thing, right? There's no difference between this x plus 4 and this x plus 4. If I had a coefficient here, something I was going to multiply by, then they'd be different, but I don't. They're the same. I could combine these 2's and I would get x plus 4. I could combine 3 and 1 and get x plus 4. I could combine these as well and get x plus 4. So since our linear functions don't have that sort of distinctive point, they don't have a corner or an endpoint like our others, I get a lot of options here for how I can write those transformations. That also means that if your transform function is different than your neighbor's transform function, that's okay. We looked at 5 different functions that could give me this line based on its parent graph, right? A lot of options here. Yep, for this particular one, yep, that would work. So we could really even do like goofy numbers if we wanted to. I could move like 1.5 this way and then 3.5 this way, and it should still end up on that line, as long as it was simplified for. Oh, g of x, that's our function notation. Since we used f of x to talk about the parent function, I use g of x for the child function. If you use f of x, that's still fine. Okay, let's take a look at a couple more examples on the next page. Same idea. This time they didn't give me the parent graph, okay? They told me my parent function is x squared. Remember, that's the one that's that sort of U shape. The important thing I need to remember, they gave me the child graph already, right? So I don't need to graph it from scratch. The important thing I need to remember is that sort of center of my graph on the parent graph is normally at the origin, okay? If I flip back to where we graphed our parent graphs, there's my quadratic function. Its center point was at the origin. So I'm just gonna plot that here so I've got that point for reference. How did I change to get the child graph? How did I get from here to here? What did I do? I went right to. So that means that my function to describe this graph would be f of x equals x minus 2 with the square outside of the parentheses. Remember, anytime we move left or right, I group that number, that whatever I'm adding or subtracting, I group it in with x. How about number 2? How did I get from my original to my new sort of center point? That point is actually called the vertex. Down 4, left 1. Down 4, left 1. So my function to describe this graph would be f of x equals x plus 1 to get me to go left 1, throw the square outside, and then down 4, so minus 4 at the end. I want you guys to try 3 and 4. Try 3 and 4. For number 3, we moved 1, 2, 3 spots left. So our function should look like x plus 3 in parentheses with the square outside. Yeah. Remember, group with x, it does the opposite. Oh. For number 4, we would move 1, 2, 3, 4 spots right. And then 1, 2, 3 spots down. So we would get g of x equals, in parentheses, x minus 4 with the square outside, and then minus 3 at the end. Questions on these two? Yes. It does not. You can use whatever function name you want. If you want to call it k of x every time, you can. Mm-hmm.
So the way to move into the side is always the one inside the parentheses for this one?
Yes. Left, right is always going to be grouped in with x. Yes. When you count, no. So if you, like here, we counted down first and then left. Here I counted right first and then down. Doesn't matter. Okay, just a couple more we're going to look at for today. On page 27, we have things that aren't described by a function. So we're just going to focus in on those transformations and the notation here. So we've got a graph here. This is our parent graph. And we want to shift it according to these directions. I've got minus 1. It's not grouped in with x. How do I want to move this graph? Go ahead. Not grouped in with x. Help us out. Yeah. So see the next one, it's grouped in with x. That's going to be a left, right. This one's going to go down. Down 1. So that means every point on this graph moves down 1 spot. And there's my transformed graph. Now, how about number 8? How are we going to move that one? Yeah, to the right too. So every point on the graph to the right too. You guys try 9 and 10 with our last couple minutes. Try 9 and 10.
This one is really taking the cross through, just go on.
Yeah. What's our transformation for number 9? What'd you say? Left. Yep. Left 3. So every point to the left 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. How about number 10? What are we doing with number 10? Up 3, right 1. Perfect. So every point up 3. 1, 2, 3, right 1. 1, 2, 3. Oops, up 3. 1, 2, 3, right 1. 1, 2, 3, right 1. 1, 2, 3, right 1. Questions for me for today? Okay. The other thing you looked at in your activity was that a value and how it could sort of stretch out or flatten my graph. It had some flips in there. We're going to talk about that tomorrow. For today, I just wanted to focus on those up, down, left, right translations. For homework tonight, you have a Khan Academy over just up, down, left, right. Okay.